schedule because Karen Halberg couldn't make it until tomorrow. So Natanael is going to talk about the role of electron-phonon interactions in quasi-2D compounds. Natanael, please.
Thank you very much. First of all, I would like to thank all the organizers for the invitation. It's a great pleasure being here again. First of all, I would like, before I start, I would like to dedicate this presentation in memoriam of Sandro Sorella. Sandro was one of my collaborators and my previous past postdoc supervisor that passed away past week. So yes, unfortunately, this is true. Yeah, yes, he was a big scientist, a great scientist with big contributions in strongly correlated physics, and unfortunately, he died. So this is my presentation is dedicated to him. Yeah. So okay, so my presentation, I will discuss some results about the role of the electron-phonon coupling in 2D compounds. My idea here is try to convince you that we cannot disregard electron-phonon interactions when discussing this kind of compounds. So I would like to, to achieve my goals. I divide my presentation this way, where first I will present you a very short introduction, and then the models, methodology, and so some results to the Hubbard-Holstein model and the SSH model, and some outlook. Okay, so I have to acknowledge my collaborators here. The results that I will present to you here were obtained, most of them by these people here. For me, collaborating with these people here, for Kazuhiro Seki, Seiji Yunoki from Riken Institute in Japan, Sandro Sorella in CISA, and Sebastião Júnior and Raimundo Santos in Federal University of Rio de Janeiro. Okay, so before I start, I would like to put a big parenthesis here just to present, just to introduce you my group in UFRJ. My group in UFRJ are all of these people here. We are the quantum matter at UFRJ. These are the faculty people. Teresa is here. You may discuss with her. Me, Marcelo, Raimundo, and Tatiana. And here are all of the postdocs and PhD master students that we have there. And undergraduate students as well. Some of them, I'm very happy to invite you to see the posters of some of them, because some of them are here. So yesterday, Andressa had presented her result. But today, we have 3 people presenting posters here. João Pedro, Lucas, and Maicon. And tomorrow, we have 4 people presenting results here in this workshop. So you are invited to go there and see their posters. They will be they will appreciate a lot. Okay, so close this parenthesis. Let me just start my presentation. So usually when we discuss about the electron-phonon interaction, the first thing that comes to mind is obviously superconductivity. So when discussing about electron-phonon interaction, we remember, for instance, the discovery of Carmelin ions and all of the achievements of Bargin, Cooper, and Schrieffer about the conventional superconductivity. But one thing that usually is not discussed in this context is that the electron-phonon interactions also lead to other kind of long-range order. For instance, charge density wave, that this is what I will discuss here. When we have electron-phonon interaction, this kind of interaction can lead to charge modulation. And basically, this coupling can create like regions with more electrons and less electrons, and this in such a way that you have long-range order. And this leads to metal-insulator transition and one permanent distortion in the lattice. And this kind of phase of state was previously analyzed by Pius. Pius was the first one to give some mechanisms to this kind of problem. So he showed that if you have a nesting in your firm surface, you have one divergence in your electronic susceptibility, and then any electron-phonon coupling that you put in your system leads to this charge modulation. And this happens in nature, indeed. This was my talk here 4 years ago about the nature of charge density wave. But this is not the whole history, because there are many materials that does not follow this Pius mechanism. For instance, this is one of them, this transition metal chalcogenides, that they have strong electron-phonon interactions, but they don't have firm surface nesting, but they present charge density wave. This is one example. This is the niobium desalinate. So this is not Pius-like, but it's driven by electron-phonon interaction. So there are many other features about the electron-phonon interaction that we don't know, and this should be analyzed. Still concerning this transition method chalcogenides, we can adjust such kind of phase by many ways. For instance, by disorder, by gate-induced, by pressure, and then we can create all of the phase, rich phase diagrams by this kind of adjustments. And again, all of these phases here, in principle, these charge density wave phases are not conventional in the sense that we cannot explain them by the Pius mechanism. Okay, so let's move on and discuss another 2D, quasi-2D material, the cuprates. When you talk about the cuprates, obviously, everyone here will agree with me that we believe that cuprates are, the phase that we have in cuprates are driven by electron-electron interactions. But this is not the whole history again. If you look here, for instance, this is a very known result for 20 years ago that shows by ARPS measurements the dispersion of the electrons in cuprates. And we see that we have a kink here, and this kink is exactly at the phonon energy of your plane oxygens, in plane oxygens. So probably this kink here comes from the one coupling with the phonons of the plane. So there are indeed one coupling. There is indeed one coupling between the electron and phonons in cuprates, although we believe that the phases are driven by electron-electron interactions. Again, recently we have seen that the electron-phonon interaction is even more important in cuprates than we thought. For instance, this is one example of on a class of cuprates that when you start doping with oxygens, we see that from I believe this is STM, we can see the formation of the gap. And the formation of the gap is completely inhomogeneous. And when we look where the oxygens are, actually here is, the important one is this one here, that is the interstitial oxygens. So we see that the oxygens are exactly at the same regions that we have the gap formation. And this kind of oxygens, this interstitial oxygens, does not lead to doping. They basically leads to a structural distortion. So obviously here that we have some kind of effect coming from the electron-phonon interaction. If this is the main force leading to superconductivity, obviously that we don't know, but there are some strong evidence to this electron-phonon interaction. I will not go deep in these details here because I'm not so expert on it, but if you want, one of the students of our group here, Victor Velasco, that's here, he's finished his PhD exactly in this kind of systems, performing some kind of, developing actually some kind of elastic nuclear theory to explain this kind of thing. Okay, finally, still discussing about cuprates. A very recent result for some kind of cuprates that you have like weakly coupled chains. They analyzing this by ARPs. They see that they can only explain the energies that they measure if they include in their model attractive interaction, nearest neighbor attractive interaction between electrons. So in other words, just the Hubbard model is not enough to explain superconductivity in cuprates. You have to put long-range interactions. And this is one of the ideas of Doug Scalapino in this review, in which they mention, he mentions that the electron-electron interaction in cuprates should have attractive interactions for nearest neighbors. And also he explained this by adding phonons. So the phonon energies can give this to you. If you want to discuss a little bit more about this, we have also one student that is presenting a poster here that will present some results to the extended Hubbard model that can in principle, explain some of these features. Okay, so, and finally, discussing the most well-known compound in 2D compound, the graphene. We know that in graphene, the electron-phonon interaction and the electron-electron interaction is not so strong, and we can explain why the graphene is metallic, discussing this kind of thing. But when we have the bilayer, the twisted bilayer graphene, we have basically these flat bands here, just a cartoon. You have these flat bands, and the flat bands, the inclusion of the appearance of these flat bands leads to strong electron-electron and electron-phonon interaction. So we cannot disregard the electron-phonon interaction here. And indeed, the superconductivity here, many people believe that this phase comes from electron-phonon interaction. So the whole history is we cannot disregard electron-phonon interaction when discussing 2D materials, 2D quantum interacting materials. And the main idea of my talk here is trying to analyze what are the effects of the electron-phonon interaction in some LETS models. Because usually, if you look at the history, people have analyzed the Hubbard model, periodic Onson model, and so on and so forth, but have disregarded the electron-phonon interaction. So here, what I would like to do is including this and trying to understand how this interaction affect long-range order. So this is the main idea of my talk. I will do all of this performing quantum Monte Carlo simulations for all of the results that I will present to you. Okay, so let's model. So as I told you, the idea here is to perform, how can I say, toy models. So we will discuss about the Hubbard model and holistic model and so on. So how can we discuss about this? So we have a lattice, so this is a pictorial view, which I will put here phonons. So the phonons to me are basically harmonic oscillators that are vibrating in my lattice. And I have also electrons. These electrons can hop from one side to the other. And these electrons also interact when they are local. So they playing the role of the Coulomb interactions. So here we have the Hubbard interaction. You also have the electron-phonon interactions because of the harmonic oscillators that we have in each side. This model is known as the holistic model, well, actually the Hubbard holistic model, in which we have the kinetic part here, the electron-phonon part here, the local harmonic oscillators, and the Hubbard interaction. But there are there are another model that we can use. This is not the only one. The another one is, again, let's come back to the LETC, put phonons here, but the phonon can instead just change the chemical potential, the local chemical potential. The phonon can modulate the hopping. And if the phonon modulate the hopping, for instance, you have oscillations that put the atoms closer, the hopping is stronger here. If they put the atoms far away, the hopping is weaker here. So this kind of problem here, again, put in the Hubbard interaction, is called, that modulates the hopping, is called the Suhl-Sharif-Heger model, the SSH model, in which the coupling here is, the electron-phonon coupling modulates the kinetic term. This K here is the kinetic term. So in my talk, I will discuss these two models, the Hubbard-Holstein model and the Hubbard SSH model. Most the first one. The later is, I have just some preliminary results. Okay, to describe the phases in this kind of systems, I have basically to study the structure factors, the spin-spin structure factor, the density-density structure factor, and trying to investigate if I have long-range order or not in this kind of problems. Also, the susceptibility, the pair susceptibility if I have superconductivity. Okay, so I will skip this part. This part is just about the method. I use two kinds of methods, the finite temperature and zero temperature auxiliary field. But this is, we can discuss later, just to save time. Okay, so let's start discussing some results in the first model, the Hubbard-Holstein model. Okay, so if we think about how the phase diagram will be, basically we can draw this phase diagram here. That's obviously, if I have a very strong value of U, probably I will have antiferromagnetism. If I have a very strong electron-phonon interaction, probably I have CDW. So this is something expected. The problem is what happens in the middle. So what happens when the electron-phonon interaction and the electron interaction are taken by the same food? Okay, so this is my first goal here, is trying to build this phase diagram for the Hubbard-Holstein model at the square LETC first. Okay, so in order to do this, I have to define one, this is something technical, sorry. I have to define one quantity that I call the correlation ratio. This is something proportional to the correlation length. And we use this as something similar to the Binder cumulants if someone does Monte Carlo here. So basically, the crossing of this quantity gives us the critical point. So we have analyzed this, starting with very large values of U and decreasing the values of U. And the crossing of this quantity gives us the critical point. So we have indeed a magnetic critical point here for a given value of U. If we do the opposite, for instance, starting with large values of electron-phonon interaction, we also have the same crossing, but the crossing here is not so beautiful as this one here. But we have also the crossing, and we can define the critical point. In other words, if performing one... what is delta Q here? Is the next... yes, exactly. The Q here is the dominant wave vector, and delta Q is just the neighbor. Yes. And so here we can perform a finite size scaling analysis in order to see it in the thermodynamic limit. And we see that, for instance, for a given value of parameters, we have one region where we have antiferromagnetism, a region that we have CDW, but there is a region in the middle that we don't have neither CDW nor antiferromagnetism. And if we perform this analysis for many other values of parameters, we are able to create this phase diagram here. So there are just few points here because it's quite difficult to obtain this data. But we are able to create this phase diagram where here we have antiferromagnetism indeed, here we have CDW, but in the middle we have one phase that is nor CDW and neither antiferromagnetism. And this phase here, unfortunately, we are not able to present with very precise results about this, but we have strong evidence that we have superconductivity here. We have analyzed, sorry, I have to come back here. We have analyzed many different types of wave symmetries. And in this case, the one that we have noticed that's the dominant one is this S wave, but it's not on-site to S wave because of the Hubble interactions. It's a nearest neighbor S wave symmetry. This is called S star wave. Yes, half filling, yes. Because away from half filling is horrible because of the sign problem, yes. Here we still have sign problem, but we can deal with it. And this result, just in parallel with us, some people from Harvard, they already presented one phase diagram to this model, where they also presented this very similar, but this is not quantum multicolor, they performing some kind of Langevin transformation using a cluster, a kind of cluster mean field, something like it. And but the phase diagram is quite similar, but the difference that in the middle here, they present a D wave, not a S wave. So we differ about this. But I will not complain because we cannot present our result so precisely, so there's no problem with it. I believe on that. It can be D wave. So this is our first result. When we move on and try to analyze it on the honeycomb Oh, no, this is, yeah, sorry. This is because I took this picture from the paper, and in the paper, this dashed line corresponds to this result here.
Yeah, the next graph, I mean, you have lambda equal, sorry. And the next graph, if you look to the lambdas equals 2, you have nothing special, it seems to me, like it's the same thing that lambdas equal 1, right? I mean, there is this kink in the plot. In the pair correlation.
Yeah. Oh, no. Yeah. No, here is the kink is one evidence of that you have superconductivity because it diverges.
Yeah, I see. But why is that marked on the U, versus lambda graph, right? Because I see that this is special because you have superconductivity, but lambda is equal to 3 and 4 doesn't appear.
Okay, no, you can discuss it later. This is something that's, there is some suitable things here.
Okay, I see. Okay, thank you.
The formation of bipolarons and things like it. This is quite, the same thing that you have asked will appear in the honeycomb lattice, but this is a little bit more complicated because of the appearance of bipolarons. Okay, we have repeated the same analysis to the honeycomb lattice, but the honeycomb lattice is completely different because we change the dispersion. We have Dirac fermions. And I will skip all of the details. I will show just the final result. This is the phase diagram in which in the middle part here, we don't have superconductivity. We have just a semi-metal, and this connects to your question, because if we increase more and more the value of lambda in U, we can have superconductivity, but I cannot access this part of the phase diagram because of the methodology that I used. But the most interesting thing here is that these critical lines, they are quite susceptible to the phonon frequencies. If I change the phonon frequencies here, for instance, from 0.5 to 1 to the square root of 2, the critical lines change a lot. In the sense that these critical lines in the honeycomb, in graphene, let's put it this way, it's quite dependent on the frequencies of the phonons that you have in your background. So we cannot disregard it because depending on the kind of the phonons and the energy of these phonons, these critical points may change a lot. So if you are interested to analyze graphene, and in particular twisted bilayer graphene, my suggestion is, please do not disregard the phonons. They can be important to your analysis. These results are already published in these two papers. You can see other details there about the universality class and things like it. I will not discuss it here. Okay, the second part of my talk, I have like 5 minutes, so I will just finish my presentation. But the second part of my talk is concerned to the SSH model, not the Holston model. The SSH is this one that you have this kind of modulation of your hopping because of the phonons. And this work is being done by one of our PhD students, Sebastião Junho, that is here. You can discuss more with him if you want. But basically, let me just remind you the Hamiltonian. The Hamiltonian is this one where the electron-phone interaction is modulated by the phonons. The hopping is modulated by the phonons. And there is one very interesting thing here. And this is something that I can ask you if you want. Do you know why we don't have superconductivity, high temperature superconductivity for conventional phonons? The question is the mass of the polarons. Because if you increase more and more the electron-phone interaction, the BCS theory would like to increase more and more the critical temperature. But you pay a price. When you increase more and more the electron-phone interaction, your electron, dressed by your phonons, becomes heavier and heavier and heavier, and then you cannot increase the temperature. This is the basic idea why you don't have high temperature superconductivity mediated by phonons. But recently, in a class of papers produced by Mona Bercil group in Vancouver, they have shown that this SSH model leads to light polarons. Light polarons in the sense that you create your dressed electron, but this quasi-particle is not heavy, in the sense that you can, in principle, leads to high temperature superconductivity. Okay, so then my question is, okay, so am I able to analyze high temperature superconductivity for this kind of system? Probably, but this is a challenger problem, so I will not pretend to say that I have the answer because I don't have. So I will save this problem to later. So I hope in a couple of years I can show you the result. But I can change the question. The question that I can change, can I try to analyze a long-range order for other kinds of collective modes, such as valence bond solid or charge dense wave? Because the mechanism is the same. If I can have high temperature transitions to valence bond solid or charge dense wave, probably I can have the same for superconductivity because the mechanism is the same. So, and this is what Sebastião is doing in his PhD. We are analyzing the formation of valence bond solid, and we can analyze it by bond-bond structure factor. And I will skip all of these details about Monte Carlo stuffs, but basically we can investigate the transition, analyzing this by the Potts equal 4 model, Potts Q equal 4 model, and we can collapse the data and see the critical exponents, blah, blah, blah. And the main result that they presented, Sebastião has shown, is basically we have this phase diagram, finite temperature phase diagram, in which the temperature increases a lot. And this is a lot indeed. I will show you one result to you compare. For instance, here is the phase diagram for many different kind of lattices for the Holstein model. And in the Holstein model, we cannot assess such kind of high temperature. And more, we have a maximum. And the maximum is because of the creation of this heavy polaron. And here, we don't have this maximum, although we have much more larger values of interactions. So these two axes can be compared directly. So this is a very clear indication, at least for us, that we can have high temperature collective modes in this kind of problems because the mass of the polarons are light. So this is the main idea. So what next? We would like to analyze it away from half-filling, because this is for half-filling. So away from half-filling is probably where we can find superconductivity in high temperature. This is not to explain cuprates, please. But we can at least try to understand why some compounds has higher temperature larger than 20 or 30 Kelvin. So this is the question. Can you have high temperature phonomediated superconductivity? Probably, if we analyze this kind of systems. So this is my main talk. I will finish just with some outlook. There are many other problems open, so about the SSH away from half-filling, frustration effects. For instance, now we have these many compounds, that's Kagome-like compounds, that they present superconductivity, so maybe the phonon can play an important role. Electron-phonon coupling, momentum-dependent electron-phonon coupling, and how the spin orbit can affect this, because this transition method chalcogenide, they have a strong electron-phonon spin orbit interaction, and the spin orbit interaction can kill the charge modulation. So there are many other problems open, so we can discuss later. So thank you very much.
So thank you, Natanael, for this very nice talk. So questions?
Well, thank you for the talk. I'm puzzled by the high temperature phono interaction. What about the hydrides?
What about?
The hydrides.
Hydrides?
Yeah, the high pressure hydrogen.
Oh, okay. No. I probably will say something that I don't know, but to the better of my understanding, these high temperature hydrogen compounds, they are phonomediated. Yeah. But the point, this is completely conventional. The point is because the pressure is so high that you can achieve such kind of high temperature. But maybe Valber can explain better to you, because there are some points that I do not know.
I thought the pressure was to get them metallic first, so that they could then become superconductors, and then it was plain vanilla sort of BCS, but I don't know. I think it's Matteo Calandra's talk. I don't know if Marcello knows more about this or not.
Not much more what to say. I know that these are light elements, so in fact, these are light. That's the reason why you see them so often. But to increase the pressure, increases also the phonomediated couple, right? Yes. I have not think about, but this is something that I can try to see for the future. Thank you.
Natanael, do you know what's the mechanism behind the formation of these light polarons, even though you have like a strong electron-phonon coupling? Like you have the effective mass in terms of lambda.
Yeah, you mean this plot?
Yeah. How do you achieve these light polarons with strong electron-phonon coupling?
I don't know exactly, but the point is that the dispersion of your electron-phonon interaction plays an important role. If you put, for instance, Holstein, but with any kind of dispersion, it doesn't play any role. You still have a heavy polaron. But for SSH, for some reason, you have light polarons.
Dispersion of the phonons? Or
No. The coupling with the hopping is the one that modulates your dispersion of the phonons, and then this plays some important role. I don't know all the details, but it's something in this direction.
Natanael, thank you for this talk. I have a question about the length of the chain. What is changed with you use odd length chains?
Here, we investigated problems in 2D lattices. And usually, because we are doing quantum Monte Carlo simulations, and for quantum Monte Carlo simulations, you cannot increase as much as you want. But for some of the biggest values of lattices that we have achieved was for the honeycomb that we performed in 30 by 30. So it's 1,800 electrons. So this is the biggest value that we achieved.
Thanks for the talk, Natanael. It was very nice. I was just wondering if you know if there's any compound or any material where the electron-electron interactions can enhance the electron-phonon coupling, if you have this kind of modulation.
No, no. No. No, I don't know. I really don't know. The opposite is true. So the electron, because what happens is, I just want to explain. The point is, you can analyze all of the electron. You can integrate out the phonons using like Lang-Furjof transformation, and you can see that this kind of electron-phonon interaction can be understood by just electron-electron ones. So this is why people still analyze extended Hubbard or long-range Hubbard, because this kind of interactions, although they are retarded one, you can still perform a transformation and analyze this by means only of electron-electron. But the opposite, I don't know. The opposite, I don't know if it's true.
So you mentioned that the problem with increasing TC by increasing the electron-phonon interaction is the fact that the mass increases. I'm old enough to have learned from the old masters that the problem usually is that there is a structural transition before you can increase TC. In other words, you have valence bond solids here. So I guess the point is, I think the question is whether you can increase TC before you go CDW. And
Yes.
I think that's the real problem that you face trying to increase TC by increasing the electron-phonon interaction.
No, I agree. I completely agree. Probably I oversimplify my argument, but my argument was on a theoretical point of view, that what happens if you increase more and more and more? Oh, okay, your mass will become, your polar mass will be larger and larger. But you are right. From an experimental point of view, if you increase more and more, you have CDW formation, then you have an insulator, so it's impossible. Yes, so I agree.
I have a question about the superconducting state you find in the Hubbard-Holstein model. You mentioned is S-wave. Can you say if it is BCS-like or is unconventional, or you don't have access to this information?
I don't have access to this, but what I have access is basically the pairing susceptibility. So I analyze, so let me come back here. What I analyze is basically this quantity in which I analyze the susceptibility of pair formation, and the divergence of this quantity give us exactly. So, but what I found in my analysis, but my analysis in this point has sign problems, so it's a mess. What I found is that S-wave, in particular, this, oh, sorry, it's not this one, it's this one here, the next near neighbor S-wave, what people call as S++. There are many flavors of symmetries. But this one is the one that is dominant and diverges. This is what I found. But it doesn't agree with this paper from Dendler group, in which they perform, it's a very, very clever thing. They perform a Lang-Frishoff, and then they analyze it on a, on a 4x4 lattice, but already integrating out the phonons. So they don't have retarded effect and blah, blah, blah. And here they find D wave. So the D wave is dominant for their case. But okay, this is something that's still open. I don't know the symmetry, but I would say that the superconductivity here is unconventional because of the effects of the Hubbard interaction. Because even in my case, that is S wave, it cannot be conventional just for the phonons, because the symmetry is not local on site. The regular on site is not local because of the Hubbard interaction. The Hubbard interaction inhibits the creation of pairs very close to each other. So you have to put a little bit more far away. I cannot find the gap. Yes, probably they can find the gap. I cannot. I don't have access.
Okay, one last question here.
Thank you. Short question. So can you tell us about the case of SSH phonons? You said you had some preliminary results.
Yeah, yes, this is the preliminary result. This is our result. What we did was we analyzed the structure factor, the bond-bond structure factor, and we did it for different lattice size, and then we performed some kind of data collapse to investigate where the critical point is, because if we are in the critical point, all of the data from the order parameter should collapse in the same curve. So this is what we did here. And the critical exponents we already know, because this is Q4 pots like universality class. We can discuss it later. Some people doesn't agree with me, but I have some strong reasons to believe. And then doing this collapse, we are able to provide the critical temperature. So this is what we present here for 1, 2, 3, 4 points in this case. So
yeah, but this is for U equals, I mean, in the
yes.
Do you have the slab, a superconducting slab in the U lambda phase diagram?
Yeah, no, I don't have so far. But this is something that we are doing. Yes, thank you.
Okay, so let's thank Natanael once again for his nice talk.